What is a buck-boost converter? In this tutorial, I will explain buck-boost DC to DC converter circuits that can be used to step up the input DC voltage or step down the input DC voltage to specific DC voltage levels. Since a buck-boost converter allows the input voltage to be either stepped up or stepped down, hence it is named as buck and boost converter or buck-boost converter. How does a buck-boost converter work? When the switch S is closed, the input voltage Vin is blocked by the diode D, since D is reverse biased. Therefore the voltage has no other option but to flow through the inductor L. The inductor L, due to its inherent reluctance property, initially tries to block the current. Due to this, initially the voltage drop across L is high. However, slowly as the reluctance of the coil decreases and the current through the inductor increases. During this phase the inductor L stores the energy, voltage and current inside its winding. When switch S is now opened, the voltage VL stored inside the inductor reverses direction, and it passes through the diode D, which is now forward biased. In the process, VL also passes through the output capacitor and charges it fully. During this phase the output capacitor stores energy inside it and gets fully charged. Simultaneously the load across VOUT also gets the energy from the inductor for TS operation. Next, at this point if the switch is closed again, the process repeats as explained. However, now the capacitor provides its stored energy to the load. Depending how fast or how slow the switch S is closed and opened, the output DC can be a stepped up or boosted output, or it can be a step down or buck output. In a real-life electronic buck-boost circuit, the switch S is replaced with a BJT or a MOSFET, and this device is switched on/EOFF through an external PWM for generating a buck or a boost output. Two-transistor buck-boost converter circuit. This circuit shows how a very simple buck-boost converter could be built using just a couple of transistors and a few other passive parts. Here the circuit is configured to provide a negative boosted output from a 5 volts input to negative 12 volts output. As soon as the circuit is powered, the T2 switches ON via R3. This allows T1 to also switch ON through the negative base bias received via R1 and T2. This causes the full positive 5 volts to be applied across the inductor L1 via the collector of T1. The inductor, due to its reluctance, opposes the instant rise in current across it and in the process begins storing energy inside its winding. Now, slowly the inductor reluctance drops and it starts passing more and more current through. Due to this the base current of T2 is pulled to ground through the inductor and via R2 and C2. This causes T2 to shut off momentarily. Now, the stored energy inside the inductor is released back to the output across C1. C1 now charges fully and simultaneously the output is also supplied with a negatively boosted voltage. The 12 volts diode makes sure that the inverted output boosted voltage does not rise above negative 12 volts. Subsequently, C2 begins charging until it is fully charged, which allows T2 to switch on again, and the process repeats. This repetition process continues at a high frequency. The frequency of the converter is determined basically by the values of R2 and C2. By appropriately tweaking the values of R2 and C2, this two-transistor circuit could be optimized either to work like a buck converter or a boost converter. Buck boost regulator with adjustable. The buck boost converter is a DC-DC converter that uses the same concept of both the buck and boost converter, but in a simplified combined circuit. As the name implies, the main feature of a buck boost converter is its capability of making the output voltage constant even though the input voltage drops below the output voltage. That means this circuit can work both in buck and boost mode depending on the input voltage. In this tutorial, we are going to understand, design, and calculate a basic high-power inverting buck-boost converter circuit based on the popular TL494 IC, and finally, there will be a detailed animation showing the working of this circuit. So, without further ado, let's get right into it. Now, before going to build a buck-boost converter, let's learn how the PWM controller TL494 works. The TL494 IC has 8 functional blocks. One, 5 volts reference regulator. The 5 volts internal reference regulator output is the ref pin, which is pin 14 of the IC. The reference regulator is there to provide a stable supply for internal circuitry like the pulse steering, flip-flop, oscillator, dead-time control comparator, and PWM comparator. The regulator is also used to drive the error amplifiers, which are responsible for controlling the output. Note the reference is internally programmed to an initial accuracy of plus or minus 5% and maintains stability over an input voltage range of 7 volts to 40 volts. For input voltages less than 7 volts, the regulator saturates within 1 volt of the input and tracks it. 2. Oscillator. The oscillator generates and provides a sawtooth wave to the dead time controller and the PWM comparators for various control signals. The frequency of the oscillator can be set by selecting timing components RT and CT. The frequency of the oscillator can be calculated by this formula. Note the oscillator frequency is equal to the output frequency only for single-ended applications. For push-pull applications, the output frequency is 1/2 of the oscillator frequency. 3. Dead time control comparator. The dead time, or to simply say off-time control, provides the minimum dead time or off time. The output of the dead time comparator blocks switching transistors when the voltage at the input is greater than the ramp voltage of the oscillator. Applying a voltage to the DTC pin can impose additional dead time, thus providing additional dead time from its minimum of 3% to 100% as the input voltage varies from 0 to 3 volts. In simple terms, we can change the duty cycle of the output wave without tweaking the error amplifiers. Note an internal offset of 110 mV ensures a minimum dead time of 3% with a dead time control input grounded. For error amplifiers, both high-gain error amplifiers receive their bias from the V1 supply rail. This permits a common mode input voltage range from negative 0.3 volts to 2 volts less than V1. Both amplifiers behave characteristically of a single-ended single-supply amplifier, in that each output is active high only. Five output control input. The output control input determines whether the output transistors operate in parallel or push-pull mode. By connecting the output control pin, which is pin 13 to ground, sets the output transistors in parallel operation mode. But by connecting this pin to the 5 volts REF pin, sets the output transistors in push-pull mode. 6. Output transistors. The IC has two internal output transistors, which are in open collector and open emitter configurations, by which it can source or sink a maximum current up to 200 mA. Note the transistors have a saturation voltage of less than 1.3 volts in the common emitter configuration and less than 2.5 volts in the emitter follower configuration. Buck boost regulator with adjustable. The working principle of this circuit is very simple. The circuit is divided into three parts, the first one being the TL for 94 PWM controller. We are using the TL for 94 PWM controller to drive the MOSFET. This IC is configured to switch at 100 kHz switching frequency, which is suitable for this type of application. Up next, we have the circuit which is responsible for the buck boost. If we consider a generic IRF 9540p channel MOSFET, the internal resistance of it is 0.22 R or 220 milliseconds, but if we consider its complementary N-channel 1, that is the IRF 540, its internal resistance is 0.077 R or 77 milliseconds, that is 3 times less than the P-channel 1. This is the reason why we have decided to modify the circuit. We have done this so that we can use an N-channel MOSFET to drive the circuit. We use N-channel MOSFET instead of P-channel. The next part of the circuit is a differential amplifier. A differential amplifier takes in two voltage values, finds the difference between these two values, and amplifies it. The resulting voltage can be obtained from the output pin. In one of the previous projects, we have built a voltage subtractor circuit where we used a differential amplifier and explained all of its details. So if you want to learn the basics of how a differential amplifier works, the video "What is a differential amplifier?" see. Finally, the resistors R19 and R20 form a voltage divider that feeds back the voltage to pin 1 of the TL for 94 IC that regulates the PWM pulse depending upon the load condition. R19 is a 10 kilo ohm multi-turn potentiometer that you can set to adjust the output voltage.